Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on January 23, 2026, just about a week ago. It presents a diffusion-based framework that excels at extreme dynamic view synthesis, allowing for the generation of coherent videos from arbitrary camera angles given only a single input. The paper is titled AnyView, Synthesizing Any Novel View in Dynamic Scenes. And, as we'll see later, the results show it can maintain spatiotemporal consistency, even when the virtual camera moves dramatically away from the original view. Figure 1 illustrates the model's performance across diverse domains, specifically driving, robotics, synthetic scenes, and human motion. On the far right, the camera trajectory visualizations reveal the difficulty of these tasks because the target viewpoint often differs drastically from the input. While the baseline methods in the middle columns frequently fail, producing blurry artifacts or geometric distortions, the AnyView column generates sharp, consistent video that closely mirrors the ground truth. Figure 2 details the AnyView architecture. On the left, two parallel streams prepare the data. The top row processes the clean input video, while the bottom handles the noisy target view. Crucially, the system encodes camera information as plucker embeddings, a dense ray-based format that helps the model understand complex 3D geometries better than simple coordinates. These embeddings are concatenated with the RGB data and stacked into a unified block of tokens. In the center, a diffusion transformer iteratively denoises this sequence, using 3D rotary positional embeddings to maintain consistency before decoding the final video frames on the right. So Figure 3 breaks down the diverse data mixture used to train the model. The chart organizes sources into 4 quadrants: robotics in green, static 3D scenes in orange, driving environments in blue, and an other category in purple. This spans inputs from robot manipulation to autonomous driving footage. To balance these, the authors apply weighted sampling so each domain contributes exactly 25% to every batch, preventing any single dataset from dominating the learning process. With the training dataset, Table 1 outlines the comprehensive testing landscape, introducing the new AnyView bench. The top rows cover traditional narrow benchmarks, where viewpoint changes are small. The authors argue these are often too easy, so they introduce the extreme categories below. The middle block details in-distribution tests, such as Droid and Waymo, where the model knows the domain but faces difficult camera trajectories. The bottom section presents the hardest challenge: zero-shot datasets like Argoverse and assembly hands, which measure how well the model generalizes to completely unseen environments. Alright, Figure 6 displays the results on these extreme benchmarks, split into driving scenarios on the left and robotics on the right. In each block, comparing the prediction columns to the ground truth reveals strong performance, even in the zero-shot settings shown in the second half of each section. The authors highlight the top left driving case, where the model correctly predicts a red car entering the intersection in a novel view, effectively inferring dynamic objects that were not fully visible in the input frame. Complementing those visuals, Table 3 provides the quantitative breakdown for the extreme DVS benchmark. The data is split into 2 groups: in-distribution datasets, which were part of the training mix, and zero-shot datasets at the bottom, which strictly test generalization. Focusing on the rightmost column, AnyView achieves the best scores across the board. For example, in the in-distribution average row, it hits a PSNR of 17.8, clearly surpassing the baselines that hover around 13 or 14. This advantage holds up in the zero-shot section as well, confirming the model's ability to handle unseen environments effectively. Well, Figure 9, in the supplementary material, visualizes how the model handles ambiguity. The layout shows an input frame, 3 independent predictions, and a heat map where brighter colors indicate higher uncertainty. Take the top row. The camera views a black bin, but the inside is occluded. Consequently, the model fills the void with different plausible objects in each sample, which lights up the uncertainty map. In the driving scene below, we see the opposite effect on the right side. Since those buildings are visible in the input, they remain stable and consistent across all generations. Wrapping up, 2 takeaways stand out. First, data-driven diffusion models can outperform explicit reconstruction methods, especially when generating views far from the original camera. Second, this robustness opens new doors for robotics and world simulation, where consistent 4D understanding is critical. That's it for this episode of the AI Research Roundup. I'm Alex, thanks for listening.